Oh, okay. Yeah.
All right.
All right.
Okay. I'm gonna share my screen.
Yeah.
Okay, so what I was thinking about doing is pretty much using something similar to a variational autoencoder. But instead, like I was explaining earlier before we started the recording, instead of having the inputs and the outputs be the same, I was thinking I would use the same structure of the variational autoencoder to turn a vector of a bunch of pretty much alloy compositions, or it could be just compositions of the material in general, and try to predict the properties from that. So I would then make a latent space. I'd use a variational encoder that would have a probabilistic latent space. I also did some research on types of regularization, and making the latent space a probability that the variational autoencoder does is just another way of regularizing it. It's a technique that's used to prevent overfitting, so that you can interpolate within data points better. So this is just the simple way to train it. You'd have a data set with the material compositions and the material properties. And I would predict the properties using the neural network. That's very similar to variational autoencoder. It's more like a translation model. I'll just call it a variational translator. And then I check and I try to train it on the loss between the predicted properties and the real properties. And so after I train it, I could just put in material properties and it would tell me stuff about the materials without actually having to go in the lab and test everything. Another way to train it, I was thinking of using the whole generative adversarial network process, where instead of maybe using like the regular loss function you use for variational autoencoders, I would use the entropy loss function. I'll explain this in the next slide, where I try to get it to predict material properties, and then I'd also have a discriminator that would try to see if my predictions and real data, and if the goal would be to trick it so that it can't tell the difference between the predictions and the real data. So I'm assuming that this model will actually work better than this because the discriminator right here will start to model the material properties as well as the variational translator. And then after computing, the same process happens. You put in material properties and it predicts what they should be like. No, yeah, you put in material compositions, and it predicts the properties. So I did more investigations on how the math works for variational autoencoders and my variational translator. So entropy loss is a loss function used for categorical variables, where you have the real probability that the variable is true, and then what the predicted probability is. And you times the real probability times the natural log of the predicted property. You add everything up together and minus its sign, because these probabilities are less than one. If you have a natural log less than one, it's negative. So the negative balances this out. So the cross entropy loss is between 0 and infinity. If you have just data points, this is probably the one that I would use. So I'd use, like I said, cross entropy for the generative to train it, and then I would use least means squared error for this one, because I'm just having material properties, and I could then check how different they are from how the actual experiments gave me, from predictions to what they actually are. And so I would just sum up all the squares of the difference between these two. Then there's okay, so I corrected this, and I apologize because I used H and G. I was going to change these because H and G are used here, which is something completely different. Um, I actually This isn't very useful because I meant to be using these instead of H and G. Um, I think this right here is supposed to be H, and this one's supposed to be G. So P of Z is G, and Z given X is H. It's basically a way of measuring the difference between two probability distributions. However, a problem with it is that if the distributions share no data points, it gives you infinity. And that's not very useful. And so there's another one that's better. It's called the Wasserstein distance. I think, Trent, you actually use this one. What it does is it measures how much work you'd have to do to move everything from one distribution to the other. The terms here are a bit complicated. I'm trying to trying to find the minimum amount of work it would take to move data points from one distribution to the next. Pi represents permutations. So there's different ways of doing something, and I'm assuming it would test every permutation and find the one that takes the least amount of work. M is moments. This is just a way of measuring distributions that aren't normal. Again, this is pretty self-explanatory. Just Z of Z1 is components in pretty much the distribution of the entire latent space, which is taken to be like a standard distribution. And Z of 2 is the data points that are particularly in the portion of the latent space that represents data point X that is inputted into the variational translator. And so the whole goal is to try to get all the data points to cluster around one large distribution so that they overlap with each other. This is important because it prevents there from being gaps where it's hard to interpolate between distributions. When you're trying to interpolate or trying to predict information that is between what your experiments give you. This is just a way of visualizing it. So you have a distribution of data points, P of X. You put that into the variational translator. You get the standard deviation, then the mean. And then this becomes, so this, right, these two right here, describe this, which is now the distribution in latent space of X. And so it's P of Z given X. And then this right here is the distribution of everything latent space given every possible input X. And then so I sample this Z from this, and then I run it through the decoder function. And then I get now the variable I'm looking for, which is the material properties, which is Y, given the point in the latent space Z. Does anyone have any questions, or am I rambling on? Does this make sense?
Yeah, it makes sense.
You can finish
Okay.
up and then I can ask the question in the beginning later. Yeah.
Yeah, same.
Okay. And so, okay, this notation, by the way, given data point X, this is a distribution of Z in latent space. This is what the notation means, by the way. And so this is described by N means a normal distribution with a mean of G of X. This is what this represents, the mean. And then standard deviation of H of X. And this will change for different data points of X, because not every data point is going to have the same distribution in Z. And then there's another way of writing it. It's the reparameterization threat that you talked about last time that helps with backpropagation. It's not super necessary for this, where you introduce a distribution, because you're going to be trying to fit H and G to be the best. And if it's probabilistic, it causes issues. But if you make something else probabilistic that you're not changing, it doesn't matter. And then so P of Z, that's actually set in advance. It's supposed to be kind of centered in the latent space, so a wide distribution or wide variance, so that it includes all the data points X. And then this is the distribution of your data that you're going to get from any data point Z in the latent space. This is what will be decoded. And it's going to have the mean be f of Z, f is the decoder. And then this is actually a thing that we could tweak. It's pretty much just the variance of the data that's given out. And then so this is the loss. So the loss is the least squares between what the actual material properties would be, Y, versus the predicted material properties, f of Z. And then plus the Wasserstein distance between the distribution of every data point in latent space versus the distribution given a data point X. And so you're trying to get these to be somewhat similar to each other, but not too similar where you wouldn't get meaningful predictions of material properties, so that you can reparameterize it to make sure that everything is a smooth continuum. Then you can interpolate stuff that is not given in your data set. And then if I use a generative adversarial network, I would use this, where it would be the probability of the material of any material property that's one measured in the lab times the predictive probability given any giving the corresponding latent space value for this. So this is just a drawing I did. It's not going to exactly look like this, but what my model will look like. So my goal is to maybe have like maybe 10 different metals, and then we could maybe tweak the device for each one. So the material properties is pretty much a vector that's length 9. It's length 9 because when you're talking about composition, the last one is you can predict it from all the others by just subtracting them from one. It's common, it's well known. So then I have the latent space here. What I do is I'd start with latent space very, very large. I don't know if I'm going to start with it small and get it larger. Whatever I do is I make it just below the point at which it causes an overfitting of data. Because it's not about compressing the data. I think I'm actually, it's not that we're going to have, it's going to be hard to like store these or whatever. It's just that this is supposed to create meaningful predictions. So I forget how to explain this, but yeah, because it's not like with the images, we're trying to make this as small as possible. I don't think that running time is going to be an issue because things we're doing is much, much, much simpler than images. It's pretty much just very simple vectors. So this could actually be quite large compared to other variational autoencoders, just so that makes meaningful predictions. And then this would be a list of material properties. I could maybe, if I only need like 2 material properties, I might not even need decoder. I could just make the latent space to material properties. But if I want a bunch, maybe like different material properties, then I could create a vector. And it doesn't, depending how many I want, it would make a more or less complicated decoder. So yeah, that's it so far.
I see. Yeah, nice. Very detailed, by the way. Didn't expect that. Yeah.
It helped because wasn't gonna just get slides on Google for this because this is very, very, very specific to what I want to do.
Very math heavy.
Yeah.
Can you go back to the first page?
Sure. Yeah.
Yeah, I don't. From my experience with like trading data, like I'm pretty sure I don't think you can just get like a new property from like in the trading process. Like I don't think it's possible for you to get like make a property with just using composition. Like usually you just split the data into like some training data set, and then because like once you put all the composition in the latent space, like there must be a way that it's linked to the property itself. Like I don't think it's possible to just like generate like properties based on how it's distributed, because it's like the model would not know how how the property works like in the latent space.
Well, the thing is, I think my latent space would actually be very, very complicated compared to most autoencoders. Depending on how many properties I have, I'd have the composition be a vector, and the list of properties be a vector too, with each spot in the vector representing a different property. We might, if it's TEC, the thermal coefficient, I might just have one property, in which case I wouldn't even need a decoder. I'd just have the latent space be about material properties. Like, what exactly are you saying? Because
I'm saying that like, aren't you saying like in this diagram that you're just feeding like the composition, like how the concentration of each metal directly
yeah,
into the latent space? Like I don't think that it's how are you gonna encode like the information like of how the properties related to the composition and concentration? Like
well, it would just learn patterns from training, right?
I see. So
Because it's turning a vector composition to a vector of a list of properties. The whole point of machine learning, right, is that it doesn't know what it's doing. It just notices meaningful patterns.
I mean,
I see. But
I
that's
mean, like,
I
possible.
mean, maybe it won't work,
But
but I think it would make sense. My
it is
latent space would be
possible.
very
Yeah.
detailed. Like it could very well actually be the same number of dimensions as the input. Because it's
Yeah.
not like I'm trying to compress anything. In fact, I want as much data as I can get my hands on because this isn't probably going to be very demanding for the machine to run a bunch of times because it's just a one vector input, one vector out. It's like an image, which has to like probably be a vector of like hundreds of thousands of inputs. This is like 10.
so wait, so you're like so you're saying like you're tuning the latent space such that you just put in a concentration and it'll generate like property
Yeah,
of
and
it?
I'm probably gonna have a very detailed latent space.
Yeah, but that
It could be like 10 dimensions.
yeah, but that latent space will be like too biased though, right? If you add like a new composition, how are you sure it's gonna adjust based to the produce the
So
right
that's
property?
well, that's the overfitting problem because if it accounts for every idiosyncrasy in the model, it's not gonna actually tell you anything meaningful. That's overfitting. So what I do is I try to make it just small enough where it's not overfit. Isn't like the whole goal if you have like n data points, you're supposed to fit it with a polynomial of n minus one terms. where it's just flow, how much data points you have, so it's not like taking noise into account. It's probably something I have to test a lot of times. But I mean, yeah, it might not learn the relevant properties. I'm assuming that it's going to like find or empirically model the equations that you would need to know to
Yeah,
predict these stuff.
yeah.
Does that make sense?
I'm just thinking about like my experience with this. Give me a sec. I'm thinking
Maybe you
about.
could ask Cal. Like, what have you done with this sort of thing?
Yeah, usually we just split like the data set, or like we include the property, like which is the final like the goal, as it's included into the data set, and you're feeding the entire, like you're splitting some of them into training set and some of them into testing set, and you feed all training set into the model, and then based on result from the model, it predicts. Hold up.
Well, you mean maybe I'd feed it half the data set and see how well it predicts the rest of the data set? I mean, that would be a good way of testing if it's meaningful or not.
Yeah. Wait. I'm getting confused. I'm getting myself confused. One sec. I want to look at my old code.
Yeah. That's normally how it works. Yeah. You feed it half and then you train the model. Then use the other half to confirm it. But
Yeah.
like even that, like this is possible, but I think it's very probable. Like it needs a very large amount of data. We don't have it.
Yeah.
But like if it works, like the paper doesn't have to do that complicated. They're just gonna use the model to predict everything. So yeah.
What paper do you mean?
The autoencoder paper.
Yeah, that was
Like that,
weird.
yeah, they have to do
I don't even know
ordering.
what they were doing.
Yeah. But what they were doing is they tried to get the latent space, and from the latent space, they can predict like the likelihood of getting a good TEC.
Yes, it looks like they would like interpolate within the data within latent space because they would just train it on composition. So what I saw in latent space though is that it seemed like the spots that are good were very spread out. Like it wasn't like they're clustered in one area. It just didn't seem like it would be a very good technique. Mine would be you could maybe test millions or thousands of different combinations and then see which one's the best, and then test those in the lab.
Yeah. But like they combine computer with lab, so it's probably different from us.
I mean, it's not like my model would be used to test stuff that wouldn't even be tested in the lab before it was used. This would just be
Yeah.
a tool to just help people narrow down their search. Like, even if it's not very good, it would still save a lot of money, something like this.
Yeah.
Oh,
Yeah.
I want to point out one thing. Like, yeah, it's what you wrote there is correct. Like, we don't include the property inside the composition. Like, but this means that we need like different latent space values for each different property we want, because it's tuned differently. Like, usually only predicts one at a time, I think, which is why like you can predict HTC or whatever. It predicts
Well,
one at a time.
I mean, some of these properties are independent from one another. Like maybe I'm trying to think. I'm trying to think of an example. Like maybe bulk modulus or tensile strength or density. Just take those three.
Yeah, those might be related.
No, I take back the independent part, but it's sort of like a program could predict all three.
I think it's
I
a
don't
bit
know what I'm
too
saying. Like I don't because I'm just pretty much think about it this way. I'm turning one vector into another vector, and I'm trying to notice patterns between them. And my latent space could very well be the same size as those vectors. It's just this isn't like a compression technique. It's designed to be a compression technique for images. I'm not using it to do that. I'm using it to predict materials, and I'm using the variational aspect of it as a regularization feature to prevent overfitting. To keep the data clustered in ways that are more meaningful, so you can interpolate better. I mean, maybe not. We'll see.
Yeah.
But if it was just like maybe one property, I wouldn't have a decoder. I'd just have the latent space be a probabilistic prediction of what those properties would be.
You're right. Yeah, it might. I feel like neural network could probably predict multiple at a time. But I'm just
because what it like think about like the latent space maybe is like the very important things you need to know about those metals, like the very basics. But those would tell you everything about their characteristics, and so you can get different properties from that. Because the whole point of like machine learning is just to recognize meaningful patterns very
Mhm.
quickly.
Yeah.
It'd be
Yeah,
interesting. Do you know if there are any like graduate students in Cal's group where I can maybe run this by who've done this like a lot?
I have no idea.
Okay.
Yeah, they have different projects, and I think one of them have simple genesis. Let me see.
I mean, we were looking at
Hmm.
Bin's paper, and there's like a CNN or something. So he probably did some stuff. Like,
That's the stuff they use to recognize images, right?
but they're kind of related, right? I mean, he probably also know about this.
Wait, I think the CNNs were predicting how atoms would diffuse, right?
Mm.
CNN
Because it
was
doesn't matter where they are in the
images.
metal, they're going to.
I don't think CNN is for this. CNN for images.
Yeah, it's for images, but it doesn't mean he doesn't know. Like, that's just one part of the paper. So he probably
Maybe, yeah,
also know about it.
yeah. Or you
Yeah.
can ask Cal something like that.
Yeah. I think Cal doesn't know that much about material science, or no, he does know he knows a lot about material science, but does he not know that much about machine learning? Is he an expert on this, or is he kind of just using it as a technique?
I mean, the graduate student using machine learning, so I bet he had to know it.
Okay.
Yeah. It's gonna be funny if he doesn't know it. Like you have your student do it, you don't know it.
Well, don't some professors like make their students do all like the grunt work while they handle like the higher up stuff? I mean,
Mm,
it kind of makes sense,
Mm-hmm.
yeah.
but
But it's a computational based tuition. I don't know. Please. Yeah.
all
Anyway.
right. Any questions? You want me to close it up, or
Yeah. All right. Yeah, that's good for me. Mm,
all right, cool.
right. Yep. That's it, huh? Anything else? Wanna share?
All right, do you want me to stop recording on my end?
Yes. I will stop.